we present continuous levels of detail for light field networks. Over the past few years, neural representations have emerged as a powerful tool for encoding data such as images, 3D shapes, and 3D scenes. Light field methods are neural representation for 3D scenes which directly output the color for each ray instead of performing volume rendering, enabling real-time rendering. Along with the introduction of neural representations, several methods have appeared that learn to represent 2D and 3D scenes at multiple levels of detail. For example, the methods listed here all decompose a scene into multiple resolution levels with regions represented by latent codes or neural networks. These methods aim to improve learning accuracy and efficiency. These methods adopt modified neural network architectures with increasing layers or widths to achieve multiple levels of detail. However, most existing methods only achieve a few discrete levels of detail. Discrete levels of detail have a few drawbacks, including artifacts during transitions, large model deltas, and the need to choose available levels of detail before training and rendering. Continuous levels of detail elegantly addresses each of those drawbacks, allowing smooth transitions between levels of detail, the gradual streaming of network weights, and real-time adaptation to available resources. The goal for our paper is to develop a light field network representation which supports continuous levels of detail with a compact, real-time MLP representation. To develop continuous levels of detail, we propose 3 modifications to light field network training. First, we propose mapping continuous levels of detail to different widths in a neural network. For this, we use a minimum width of 25% of the neurons in each hidden layer to ensure reasonable results. Since neural networks have discrete sizes, we represent the fractional level of detail by fading in new neurons. Next, we propose training with summed area tables instead of downsampled images. Summed area tables allow us to perform arbitrary scale sampling of our training images without having to cache multiple scales of each image. Finally, we proposed using saliency-based importance sampling during training to ensure that the network focuses its capacity on the regions users are most likely to focus on. To accomplish this, we estimate a saliency map for each training image and use the saliency mask to guide the sampling of foreground rays during training. Here we show qualitative results transitioning across levels of detail. Adding neuron masking allows us to render continuously with fractional levels of detail. Here we see that the leg of the card expands smoothly between level of detail 199 and 200. In conclusion, we present a light field network representation which supports continuous levels of detail. Please see our website and paper for more details.